Hello everyone, and welcome back to a new video in programming the Finite Element Method using MATLAB. In this video we are going to continue and finalize our efforts on the line key points, and we have basically reached the position where the line key points are defined, but now we need to deal with distributed loads and see if they pass above the line key point or not. Now, of course, before I start, I want to mention that this is part of a Finite Element Method theory and programming series, both linked on the top right, and that my dear channel members have access to the entire source code. However, if you're not a channel member, then don't worry, because every single line will be written in front of you and you can just write along and you'll have the exact same code as mine. So yeah, with that being said, let's dive into the video. So sit back, relax, and enjoy the show. Okay, let's continue now. We need to see all the loads and actually add them to the load key points. So here I will give a for loop and basically ask for load index equals 1 to the length of object dot str, I think it was line load. Yeah, line load distributed. So we are passing through all the line load distributeds that we have. We're gonna fish out the load. So basically I will call here linear load, and this equals the object.stir line load distributeds of load index. Okay, so we fished out the load, and now we need to do our shenanigans and tests. First of all, I want to check if it is applied on that line. Okay, so I think I can just copy one of those checks I checked before. I think I can copy it from here maybe, and then make this small and just copy and paste it here. So we are checking if it's applied on the line by checking the load we applied to, and basically saying, well, if the line we have has the load applied on it, then is applied on line, we set it as true. Fantastic. So now that's the first thing. The second thing I need to know what load case this load is about. So here I will basically say load case index. Now it's not the load case ID, because you could delete some load cases, but that's maybe something for another day. Let's focus on our task at hand here. Index equals -1 for now. And now I'm gonna go for a loop for I equals from, wait, I might have it decline different somewhere. I equals from 1 to load case count. I think that was it called. Was it called load case count? Here I will fish out the load case. I will say here if the object dot stir load cases of I dot id double equals the load linear load dot load case id, then I have it, and I can say that load case index equals I. So now we have those things. Now we ask the question, if is applied on line, then we need to deal with stuff. Here the load is applied, it will affect some LKPs. Let's find out which LKPs get affected. Before we start, we need to transform this into the local system. So now I think I can copy paste the commented here. I have commented something out, this one. I think I can copy paste this entire thing because I need the local loads, because I'm gonna apply them. Let's copy it. Let me just make it smaller because I kind of lose track immediately. It's very long now. Yes, here. So let's paste it here, uncomment. So now we have the global loads, which is from the load, linear load. We take it from the linear load. Is it called linear load? Yes. And we have the local loads. And those things we're going to use now. I need to cycle through all line key points and see if they are affected. So let's do this. For LKP index equals 1 to length of line.key points. So we're cycling through all of them. Here, I'm going to first of all fish out the LKP. So LKP equals line.line key points of LKP index. We fish it out. And now we need to ask. And there are 3 possibilities for the line key point. Possibility 1, line key point was at the start of the load, of the distributed load. And if the line key point was at the start of the distributed load, then the distributed load shall be stored in the distributed after. Option 2, line key point was defined at the end of the distributed load. In that case, the distributed load must be stored into the line key point distributed before. Option 3, line key point is in the middle of the load. In that case, we first of all need to interpolate the load value because it might not be a constant load. And then we need to add the interpolated load value into the line key point distributed before and distributed after. So let's do this in coding. Case number 1, line key point at start of distributed load. How do I check that? Well, if absolute LKP dot absolute load location minus linear load dot relative location start multiplied by line dot length is less than 20 times object dot epsilon. So if it's close to the start, you can see LKP location is close to the start of the load. This means we are at the start of the load, and I can start changing things as follows. LKP of or dot fx distributed after. For which load case? For load case index is going to equal the old value plus the local loads of 1, because we're going to apply the distributed load at 1. And why at 1? Because there is no need for interpolation, because we need the start value directly. I'll copy this entire thing and paste it 5 times and change whatever is necessary. Case 2 is if we are in the end. So I'll go and copy this entire thing and write here else if and paste. No if here. Here we're going to ask LKP. Wait, where's an arrow here? Statement under else if cannot be reached because it's duplicate. Okay, what is the same? Yeah, we'll change that. Don't worry. MATLAB is angry because we have the same condition. So here we're going to say LKP absolute location. This time it's at the end, okay? And since it's at the end, those things will change. First of all, those dudes become before, not after, because it's at the end, so we're talking about loads before. And the degrees of freedom we are copying from are not 1 to 6, but 7 to 12, because we are taking the final load values. There is no need for interpolation because we are at the end of the load, which means the value at the end is what is needed. Now, I cannot call else here. I need an else if again. And this time, I will, let me just comment and say case 2, this was case 2, LKP at end of distributed load. Now, this case is going to be case 3, and this we will call LKP at, not middle, inside the distributed load. Okay, so let's do it, ladies and gentlemen. What's the condition that makes LKP inside the load? Well, it must be more than the start and less than the end. LKP dot absolute location is more than the linear load dot relative location start multiplied by the line dot length. And it doesn't work because of numerical shenanigans. So minus, let's put an equal sign here because there is no equal sign here. So there is a case where it's exactly 20. Oh wow, that would be very bad. I don't think it exists. But due to mathematical shenanigans, I think I should put an equals here. Minus 20 multiplied by object of epsilon. Please think about it yourself. It will make sense because of numerical shenanigans. That's not enough. The start, the LKP must be more than the start, and at the same time, it must be less than the end. So LKP dot absolute location should be less or equals linear load dot relative location end multiplied by line dot length plus 20 multiplied by object dot epsilon. Yes, now that's the condition. Yes, now here we cannot simply add the distributed load. As a matter of fact, that was a bug in Strado I found out in 2023 because I was just simply adding the loads, despite the fact that if I have a trapezoidal load, it's not going to be the load value because it changes linearly. So now let's interpolate the value of the load. So let's do the interpolation. Load start, this equals linear load dot relative location start multiplied by line dot length. and load end, this equals linear load dot relative location end multiplied by line dot length. The x here is basically LKP dot absolute location, and x1 is going to be load start, x2 is going to be load end, fx1 is going to be local loads of 1. I'm preparing all the load values, every single one of them. So let me just copy this entire thing and paste it 12 times or something. So there we go. That's fy, that's fz, that's x, that's y, that's z, 2, 3, 4, 5, 6. And here, I'll copy this entire thing, paste it here, and call it 2. And here I'm going to take the 7 to 12. So 7, 8, 9, 10, 11. So now we have the load values, and now we need to get the, let me remind you, f of x equals slope multiplied by x plus intercept. So our goal here is to find the slope and find the intercept. Slope is delta y over delta x. So let's do it now. Slope equals fx2 minus fx1 divided by, I think it's x2 minus x1. Yes, that's the slope. For the intercept, that's going to be fx1 minus slope multiplied by x1. You can basically do this by equating a value of x and the value of the function and getting the intercept by solving this. So we have the slope and we have the intercept, meaning that I can now find fx interpolated. Fx interpolated, this equals the slope multiplied by the x location plus the intercept. And you can rinse and repeat this multiple times for all the load values. So I copy this and paste it 6 times. 2, 3, 4, and 5, and 6. So now we need to do the same thing for the y. So those become y's. The x's remain the same, but the y's change. And now those become z's. That's a z. That's a z, and so on. Those become mx's now. So this is mx2, and that's mx1, and that's mx. So this becomes mx interpolated. Now here we have my, which means this dude is my. And now we have mz, which means that is mz. Now we have the interpolated values. So now we need to add to the start and to the end. So what I will do here is I will copy this entire thing and paste it here. And copy the after, or the before, sorry. And paste it here. And now here, this is going to be fx interpolated. That's going to be fy interpolated. That's going to be fz interpolated, mx interpolated, and so on. And I think that's it. I think with this, our line key point generation is mission complete. Is it bugless? No idea. We will check that out in our benchmarking. But for now, line key point generation has been accomplished. So yeah, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a complete line key point sized shout out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.